Hello everyone, welcome to the next lecture of electronic devices. We are talking about MOSFETs, and today we are gonna discuss some circuit problems in which the MOSFET is used in the DC circuits. So we're gonna solve some of these circuits. Okay. So look at the example over here. In the circuit that is shown in left, we need to determine the values of RD and RS, and so that the transistor will operate with a drain current of 0.5 milliamperes. The drain voltage is 0.5 volts, right? So this is a gate terminal. The arrow terminal is always a source terminal, and the other terminal is a drain terminal. The threshold voltage is 0.7. Process transconductance parameter is 100 micron amperes per volts, length of the channel and width of the channel. And we can assume no channel length modulation effect for this example. Okay. So let's find out the values of RD and RS. So in order to find out these values, so I guess the value of the RD can be easily find out by a simple Kirchhoff law. So you can you have a value for ID, for example, right? So RD equals VDD minus VD over ID. You know the value of ID, which is 0.4 milliamperes. You know the value of VDD, 2.5 volts, right? And VD 0.5 volts. And ID is 0.4 milliamperes. If you're going to put down these values, you can easily find out the value of RD, which comes out to be 5 kilo ohms. Okay. Now let's find out the value of RS. You realize that we can find out the value of the RS exactly using the similar approach, right? So value of the RS can also be found out by using source voltage, Vs here. Vs minus VSS over ID. We already know the value of ID. We know the value of VSS, which is minus 2.5. We need to find the value of the source voltage over here, right? So let's find out the value of the source voltage. Now, since in this transistor, we can see that the drain voltage is higher than the gate voltage. So this means that the transistor is operating in the saturation region. So if the transistor is operating in the saturation region, going back to the summary slide, I can use this equation to find out the value of the overdrive voltage. Okay, so equation that I can use is ID equals half Kn dash W over L VOV whole square, and this VOV is VGS minus VT. So if you look over here, we have the value of ID 0.4 milliamperes, Kn dash, which is mu and Cox, W value is here, length value is here. In this VOV, we have a threshold value, which is 0.7 volts. And for this gate to source value, this is VG minus VS. VG is 0 volts. We can find out the value of the VS, right? So putting in all the values, we ended up finding the value of the VS to be, okay. So let's find, so this is the value of the overdrive voltage that comes out. And then we can say this is equals to VGS minus VS, VGS, VG minus VS. Okay. So a gate to source voltage is equals to the overdrive voltage plus threshold voltage, right? So overdrive voltage will be equal to, we already know the overdrive voltage 0.5 plus threshold voltage is, what is the threshold voltage here, 0.7. So gate to source voltage will be 1.2. okay, so gate to source voltage is 1.2, so this means that it will be equal to 1.2 volts. So the source voltage comes out to be minus 1.2 volts, right? So this source voltage, this will come out to be minus 1.2 volts. Now, going back to this equation, we can put in the value of Vs now, VSS and ID to find out this value, right? So this will come out to be RS equals Vs minus 1.2 minus VSS. VSS is minus 2.5. Minus 2.5 divided by ID. ID is 0.4 milliamperes. And we can find the value of the RS. Over here I did, yeah, so we calculate the value of the VS using the same equation. Our value of the RS came out to be 3.25 kilo ohms. Okay. Right, so just use this simple circuit, Kirchhoff's law, voltage divider rules. While solving any of these problems, you need to know where the transistor is operating in which region. So if you have this basic understanding of electric circuits, and you have a basic understanding of the region or the mode or the region of operation of the transistor, of the MOS transistor, you can figure out or solve almost all of these circuit problems. Okay. Now, so let's go to example number 2. Okay, so in this example, we need to find the IV relationship of this circuit. So the unique thing about this circuit is this gate terminal is connected to so this is the gate terminal, this is the source terminal, this is the drain terminal. So the gate terminal is connected to the drain terminal, right? Okay. So we know that this current that flows from here is usually ID. Over here we are calling it as an I. And our the voltage, this V voltage that is appearing over here, this voltage is drain to source. Since our drain voltage is equal to the gate voltage, so I can call this V as gate to source voltage as well for this specific case. Okay, now since gate voltage and the drain voltage are equal, this means that the transistor is operating at the edge of saturation. Edge of saturation, right? And we can use the same equation for the edge of saturation. So at the edge of the saturation or the start of the saturation, the equation is over here. You can also see the same equation over here. Use any of these equations. Essentially, this is just opening up the VOV here. Okay, right? So all you need to do is to replace this VGS by this V and this ID by the value I, and that will be the IV relationship of the circuit. So yeah, this is kind of a very simple problem on how we can make an equation of IV characteristics of this diode connected transistor in which our gate terminal is connected to the drain terminal. Okay, so let's do one more example now. And here's another example. So in this example, what we need to find out, so we have biasing voltage. We are given a drain voltage. This is 0.1 volts. Our gate voltage over here is equals to this biasing voltage 5 volts. Our source voltage is 0 volts. It's grounded, right? And we need to find out, and our threshold voltage and the process transconductance parameters over here, we need to find out the value of RD here. Okay, now if we look closely, our drain voltage is less than the gate voltage. This means that the transistor is operating in a triode region, or our drain to source voltage is less than the overdrive voltage. Overdrive voltage is VGS minus VT. So VGS is 5 volt. So the overdrive voltage is 5 minus 1, 4 volts. So 0.1 is very less or much less than the 5 volts or the 4 volts overdrive voltage over here. So this means that it is operating in the triode region. You can also verify the same thing by looking at the plot. If your VDS value is less than the overdrive voltage, it is operating in the triode region. Okay. Okay, so we know that the transistor is operating in the triode region. So let's find out the value of this ID. Right. So what is the equation, drain current equation for this ID? The drain current equation for the ID is over here, or you can use this expanded version of it in which the brackets are open. So we are going to use this equation. All right. So the current for the drain current for the triode region is given over here. That can come from the assembly slide as well. Okay, so we are interested in finding out this ID value. So let's look at that if we have other values available. Our Kn dash W over L is here. We know the value of the gate to source voltage, which is the gate to source voltage is 5 volts. Our threshold voltage is 1 volt. Our drain to source voltage, is 0.1 volts, and drain to source voltage is 0.1 volts. Okay, so by putting all these values, we ended up finding the drain current to be 0.395 milliamperes. Okay, so once we ended up finding the drain current, now you can see that I can easily calculate the value of the RD, right, using simple Kirchhoff's law. So ID can be found out by this, right? So RD can be found it out by this 5-fold VDD minus VD over ID. ID comes over here, VDD is your biasing voltage, VD is 0.1 volt. So you can easily find out the value of RD, which came out to be 12.4 kilo ohms. Okay, so we ended up finding out this value as well, RD. However, the question was, if we go back to the question, so understanding the question is important for all of your exams and other homework problems is. So what we were interested in is finding out the effective resistance between the drain and the source at this operating point. So this means that we are interested in finding out the resistance in between the drain and the source terminal. What is in between drain and the source? The channel. Okay, so we are interested in finding out the resistance between drain and the source. Okay, so in order to find out this resistance, so let's assume that so let's look at the values, right? So what is our VGS, our gate to source voltage? We saw that it is 5 volts because source is 0. And what is our drain to source voltage? Since source is 0, drain to source voltage is 0.1. Our VDS is very smaller than the VGS. And we saw that when this condition is true, when VGS is very small, when the drain to source voltage is very small than the VGS, we are looking at this region, right? In this region, our channel behaves as a linear resistance. And the value of the conductance or the resistance of the channel is given by this thing, Kn dash W over L VOV. So our conductance is Kn dash W over L VOV, which is Kn transistor MOSFET transconductance parameter into overdrive voltage. So the resistance of the channel drain to source will be 1 over Kn VOV, right? So we already know the value of the overdrive voltage because we know the value of the VGS. So VGS minus VT is overdrive voltage. The VGS is 5 volt, threshold voltage is 1 volt. So the overdrive voltage came out to be 4 volts, right? 4 volts. And the Kn value is this, the combination of Kn dash and W over L, right? So we can easily find out the value of RDS, the effective resistance in between drain and the source. Okay. And there's another way that we can find the value of the RDS as well, right? So one more way that we can find out the value of the RDS will be if we look at the circuit, right? So our resistance, this resistance can easily be also be found by VDS over ID, right? And we know that our VDS is 0.1 volts and our ID is, what was ID? 0.395 milliamperes. So we have two ways to find out the value of the RDS, and now we are going to compare the values, right? Okay, so this is what we talked about. The VDS is small, so it must be operating in the it is still operating in the triode region, but in a very early part of the triode region where the resistance of the channel is linear. So one way to find out this RDS is just VDS over ID. The value comes out to be this. The other way to find this out is 1 over Kn over VOV when channel behaves as a linear resistance. This is what we talked about over here. And the value comes out to be 250 ohms. Now you can see that the value obtained by both of these two methods is very close. Okay. Okay, so let's do one more example, quick example. In this example, let's look at this circuit here now. And what we are interested in, so here are some of the transistor parameters. The threshold voltage is 1 volt. The process transconductance parameter Kn dash W over L is 1 milliamperes per volt square. And we can ignore the channel and modulation effect. Okay, so what we are interested in is finding out all the values here at all the nodes and the voltages. At all the nodes, we are interested in finding out the voltages and the currents through all the branches. Okay. Now, if we look over here on the circuit, so essentially what I want to do is, of course, I want to find out the drain current, right, that is flowing here. I want to find out the source voltage, the drain voltage, the gate voltage. And we know that the gate current is 0. I want to find out the current that is flowing in this branch as well. We can call it as an IL. Okay. So this is what we are trying to find out in this example. So if we look at this example in more detail now, so let's look on the left side. On the left side, we have a 10 volts biasing voltage here. And then we have, since the current is 0, it's a simple voltage divider circuit, right? So the voltage will be divided equally, and what we will get over here is just 5 volts, right? You can also write a voltage divider equation in order to solve this, right? So the gate to source voltage is equal to, right, across RG2, it will be VDD into RG2 over RG1 plus RG2. To find out the value, right, and that will come out to be 5 volts. Otherwise, if the resistances are equal and they are in series, right, the potential drop across them will be equal. Okay. So we ended up finding the value of the 5 volts. We can also find out this current that is flowing in this branch, and how we can find that out by simply, right, let's assume that let's call this current to be IL. So IL would be equal to VDD minus VG over RG1. So it will be 10 minus 5 volts over 10 mega ohms, whatever the value comes out to be. So the value that comes out to be is equal to 0.5 microamperes. Okay. So we ended up finding out these values. So we have a current flowing through the left branch, and we have a gate voltage. Now we are interested in is finding out the drain current, this value, the drain voltage, and the source voltage. Okay, so in order to find out the value of the source voltage and the drain voltage, let's write down the equations. We can see that over here, the let's see, the ID will be equal to VDD, which is 10, minus VD over 6K. Assuming these currents to be in milliamperes, for simplicity, I'm going to ignore this K, kilo. Right, so what will be the VD? VD will be equal to 6 times ID. It will be, 6 times ID. VD will go on the left, ID will come on the right. So this will be equal to, okay, so it will be VD will be equal to 10 minus 6 ID, right? Similarly, the source voltage will be equal to, ID current is flowing over here, right, would be equal to 6 times ID, right? Okay, so we ended up finding out the equations for the drain voltage and the source voltage. Okay, so, right, so this is a drain voltage, and similarly here the source voltage. Okay, so by now this is what we have. This is the circuit we have. We ended up finding out the gate voltage here, VG. This is a VG. We ended up finding the current in the left branch. Here is our drain voltage. Here is our source voltage. So this is what we ended up finding out. We need to find the exact values of the drain voltage, the source voltage, and the drain current now. Now, in order to do that, again, in order to find, we can always start with finding out the drain current value, right? In order to find out the value for the drain current, we need to first figure out in which region our transistor is operating. And in order to do that, let's look at the voltage values here, right? We can see that at the gate terminal, so this is a gate terminal. So at the gate terminal, we are applying 5 volts to this NMOS transistor. and the threshold voltage is 1 volt, right? So this means that the transistor will be turned on by this 5 volts. We haven't determined the value of the source voltage, so we're going to do that. So the transistor will be turned on. Okay. Now the transistor is on, but in which region transistor is operating, whether it is operating in the triode region or whether it is operating in the saturation region, that depends on the value of the drain voltage in comparison to the overdrive voltage or the gate voltage, which we don't know. Since we don't know the drain voltage, so we are going to make an assumption here. We are going to say first, either we can select any one of them. We can say, okay, we are going to start with saturation region, and if this turned out to be okay, then if the answers make sense, and we're going to talk about what does that mean. If the answer makes sense, and we will say, okay, these are our answers. But if the answers does not make sense, then we will go back and resolve it for the other region of operation. Okay. So this is what we talked about. There's a positive voltage at the gate, right, which is greater than the threshold voltage of 1 volt. So NMOS transistor will be turned on. However, we don't know whether it is operating in the saturation or in the triode region. We will start with the assumption of a saturation region operation. We will solve the problem and check the validity of our assumption. And if our assumption is not going to be true, then we will redo it for the triode region operation. Okay, so let's start with the saturation region operation. For the saturation region operation, we know that our value of the drain current is equals to half Kn dash W over L VOV whole square. Now, in order to find out all of these, or simply put, let's see that this is half Kn dash W over L. This VOV essentially is VGS minus VT. We know the value of VT is 1 volt. What is VGS? VGS is VG minus VS. Gate to source voltage is 5 volts. What is the source voltage? Source voltage is 6 ID, right? So we are going to put 5 minus 6 ID as gate to source voltage in this equation over here, and this entire thing will go over here, right? Okay. So here's the saturation region equation. We know the value of Kn dash W over L. The VGS will be this, and we know the value of the threshold voltage. Now, putting in all the values, we ended up, it's the same thing as 5 minus 6 ID. Putting in all the values, we ended up getting this quadratic equation again. And if we will solve this quadratic equation, we ended up finding the two values, right? So the one value of the drain current that we ended up finding is 0.89 milliamperes, and the other one we ended up finding out is 0.5 milliamperes. Now we need to see which of these roots of that quadratic equation will make sense, or if any of these roots are true or not. Okay, so we will start with the first one, 0.89 milliamperes. And what we want to do is we want to go back and try to validate our assumption that we have to do over here two things, right? So one, we have two roots. We need to find out which root is that okay, and the second thing, we need to find out for which root is going to, if any of these roots will make our assumption valid or not. An assumption of that the transistor is operating in the saturation region. Okay. So this is the assumption that we need to validate, right? And we know that in order to validate that assumption, our drain to source voltage should be greater or equal to the overdrive voltage. Okay. So going back over here, this is our first root. We can start with the first root as ID equals 0.89 milliamperes, and let's find the drain and the source voltage values, right? Our VD is 10 minus 6 ID, and VS is 6 ID. Right, so what we are going to do, we are going to put down the values of both of these roots, 0.89 and what was the other one, 0.5 milliamperes, and find out the values of the drain and the source voltages, and then we are going to compare it. Okay, so let's take this value. So when we use 0.89 milliamperes and find out the values, find out a value of the source voltage, it comes out to be 5.3 volts, right? Right, so we know that source voltage is 6 times ID, so if we ended up putting this comes out to be 5.3 volts. Now we know that the transistor is on, and in order for the transistor to be on, the gate to source voltage needs to be greater than the threshold voltage. So what is happening over here is if I assume this 5.3 volts value to be true, then my VGS value comes out to be minus 0.34 volts, right? So this means that the transistor is cut off, which is not true. So we are done with 0.89 milliamperes root. Now let's check the other root, 0.5 milliamperes. Right, now we are going to check the other root, which is 0.5 milliamperes. Now when we put the 0.5 milliamperes and calculate the value of the Vs, it comes out to be 3 volts. Right, so this means that we can again do the same thing, VGS. So Vg minus Vs, gate is 5 minus 3, 2 volts, right? This 2 volts is greater than the threshold voltage, so this means that the transistor is on. Okay, so this root is okay. Now let's see that if our assumption is true or not. Our assumption was our transistor is operating in the saturation region. So in order to do that, let's find out the drain to source voltage. So what is our drain voltage? Our drain voltage was equal to, where's our drain voltage? 10 minus 6 ID, right? 10 minus 6 into ID. So we have 10 minus 6, ID is 0.5, 6 into 0.5, 3 minus 10, 7 volts. So this is the value of the drain, right? And for the source, what is the value of the source? 3 volts. So drain to source is, drain minus source will be 4 volts. Right, now we know that the drain to source voltage comes out to be greater than the gate to source voltage, or more importantly, we are interested in finding out it should be greater than the overdrive voltage for the saturation region to be valid, right? And what is the overdrive voltage? Overdrive voltage is the gate to source voltage minus threshold voltage. Gate to source voltage over here is this is the one, 2 volts. 2 minus 1 volt. Our overdrive voltage is 1 volt. Since our VDS is 4 volts, which is greater than 1 volt, so this means that the transistor is operating in the saturation region. So our assumption was true, and we are good to go. And we don't need to worry about redoing it for the triode region. Otherwise, we would have done the exactly similar process again. We would have assumed it to be operating in the triode region. We would have done the same thing, find the value of the ID, then check both the roots, which root makes sense. And then for that root, we are going to validate the assumption, whether our assumption is still valid or not, that the transistor is operating in the triode region, if the saturation region would not have worked out, and if we would have been doing the triode region. Okay, so with that, this part of the lecture is over, and in the next part of the lecture, we are going to do a couple of quick more examples, and then we will get back to the theory again. All right. Thank you so much, and we will do the second part shortly. All right, thank you. Bye-bye.